Okay, so it's quite straightforward. Just hopefully people know how to generate these Mueller indexes from this. Okay, okay, fine. So this is just example of cubic unit cell. And what about if you look down into this plane? Potentially, what do you see, right? Because let's say I look across on this plane. These are parallel plane. Right? This intercept 2A, this intercept 1A, and so forth, right? 3B, 2B, and 1B across like this. And if you look, your eye look along in this direction. What you see are these parallel plane. They're parallel plane along like this, right? And then if you look along in this direction, you may see plane like this, right? So I'm now starting to let you think about columns of atoms, right? Remember I was telling you about transmission electron microscopy, right? When you do transmission electron microscopy, you see columns of atoms, right? So why column of atoms? Because in this plane, there are layer of atoms. The atoms are arranged like this. Same with this one, okay? But in transmission electron spectroscopy, you look across. Your eye is this way, right? Your electron should be electron beam across. And these column of atoms, so of course there's a series of atoms like this lining up behind each of these, right? Another plane, another square like this, right? Going along. And of course all these column of atoms has to line up. Otherwise they may hit, they may not go straight through, right? So it has to line up. So when you look down, so this, you can imagine you're doing TEM, you're looking sort of down on this plane, and you're really seeing this one atom here. You're really just seeing a column of atoms behind the front atom here, but this really represents one column of atom, another column of atom like this. Okay, yes?
So does that mean you have to be looking directly along
Exactly.
that plane? So how do you make sure that your sample
that is a tricky point. I mean, that is what people, that is why you require skill when you do TEM. Okay, so do not get misled. When you see all this beautiful image in literature, people show individual atoms. They are not individual atoms. They are column of atoms. So in order to get this column of atoms, you have to align your crystal in such a way you see individual atoms. Okay, so you have to manipulate the orientation of your sample in such a way so that you get column of atoms. Okay, so that is the whole point about TEM. And the fact is, you are shooting across a finite thickness of material, and even though they're crystalline, you must align them. Otherwise, you would not see beautiful single atoms. You would not see that. Okay. So that is the point. Don't get misled by people who are very excited about TEM. TEM does have this limitation. That's one. So and that is one of the limitations. Sample preparation has to be very good, and also alignment of the sample has to be very good. It's not like SEM because here you're shooting electron through. Okay, so this is kind of the thing that I like to point out. Like you are looking at these plane, right? Of course, these define different plane. I'm looking at different plane across. The plane are coming out of the plane of the viewer, right? Imagine you're looking down. My eye looking down like this. So you different. So here it's just sort of notation. I ignore this direction. Ignore one of the axis direction, like the depth direction, for example. I'm calling this 1, 0, 1, 1. You know, so this is one direction, another direction. So this is 1, 1 plane, all parallel. This is 3, 1 plane, all parallel, because there are 1 unit here, right, and 3 unit in this direction. 1, 2, 3, right. So this is my 3, 1 plane, and this is 2 to 1, right. So this is kind of my 2, 2, 1 plane, like this. They're all parallel. I want people to be familiar comfortable when they see this Mueller indexes. They can sort of think, imagine what the plane looked like. I mean, that's the skill that we want to train people as a chemist to be able to imagine these material in space. Okay, so here's another example that I put out. A plane intercept at the axis 3A, 2B, and 2C, and then you take the reciprocal, divide by this XYZ by A, B, and C vector, and then you would get 1/3, 1/2, 1/2, and then you multiply by the smallest constant to make them into integer. So you got multiplied by 6, obviously, and then you got 2, 3, 3, right? 2, 3, 3. So that becomes the plane, the Mueller index of that plane. So the plane is then identified as a 2, 3, 3 plane. Okay? So that's simple enough. I hope that people remember how to do this Mueller indexes. Okay, next. I'd like to give you a couple examples maybe about some common crystal structure that you may see. So the first one, of course, people quite familiar, I hope, with this is the cubic structure, right? We learned about this in first year chemistry courses, and these are some examples. Cubic structure, simple cubic structure, not face-centered cubic or body-centered cubic. You notice that, first of all, one thing you should, a curious fact, and it's a well-known fact, is that transition metal does not have simple cubic structure. You look in the periodic table, you will never find a transition metal have cubic structure. So gallium is not transition metal. And you find cubic structure in salt, like cesium chloride, for example, and oxygen, right? Oxygen, sulfur, halogen, these are all cubic structure. You freeze all your gas into atoms like this. And of course, these are the free plane. This is the 001 or
It's
100 plane.
100, right?
Well, yeah. So people. That's another ambiguity when you read the literature. Sometimes people mean 001, but they write 100. because they are thinking in terms of cubic structure, and therefore in cubic structure, 100, 010, or 001, they are all equivalent because the free plane are equivalent in three directions. So that's another thing, right? So when you do crystal structure, what you define, of course, is quite well defined, but because they think the crystal structure are equivalent in three directions, they use this notation very loosely. So sometimes, every time people write 001, if you check the literature, let's say you want to look for a silicon 100 surface, right? You try to do a survey of the literature, you find that the majority of people write 100. They never write 001. They certainly would not write 010. You just go and do a statistic analysis of people use the word silicon 100 in the title of their article. You never find 010. I can almost guarantee you, I can almost bet you a beer on that. Very rarely people will use that because it's kind of hard to say. Right? It's hard to say 010. It's kind of odd, right? People say that. So usually they say 100. And you'll never find, very rarely they also say 001. It doesn't sound very good. They say, oh, the Mueller index playing 100 or something. They don't say 1, because 1 is very hard to say. So that's what it is. So even though, of course, this is 001, in technically it means that the